Carnegie Mellon University. He's a member of the Human-Computer Interaction Institute, and his research integrates data visualization and machine learning techniques to create visually interactive systems to help users make sense out of large big data. And so he works in the human-centered data science domain, and that's what his talk is going to be about. He has also previously worked as a research scientist at IBM Research, and he has done his PhD in computer science from the University of College Park, Maryland. So with that, we will let Adam take it from here. Thank you. And thank you for accommodating, last-minute changes. All right.
There you go, if you can just put it on your tail. Is it working?
I need to plug in first, which
Right.
is this. Then.
Your dongle.
All right. That's the wrong dongle.
We have the fancy one over here.
Oh, okay. Yeah.
We have it.
This might be it.
The fancy one.
Let me actually just.
Yeah.
All right, so let's see if that works. Okay. So thank you for the kind introduction, and thank you for inviting me here to Virginia Tech. It's my first time on campus and a beautiful place to be, so really excited to be a part of today. So I'm going to be talking a little bit about, so I'm a data visualization person. That's kind of what my home community is. And so I'm going to be talking really about kind of how do you take a data visualization approach to understanding algorithms. And so over the course of my PhD, my stint at IBM Research, and now at CMU, I've built lots of different types of data visualization tools. I'm not going to talk about them. This is just kind of, again, an ugly collage I put together this morning about just taking some screenshots of systems that me and my students have put together over the years. But really, they're really good at empowering people to make sense out of information. And so if you put these tools in front of someone, and I'll just call them broadly now a data explorer, oftentimes you'll show them this tool, they'll go, wow, I've never seen my data like that before. This is awesome, and they're happy about kind of the insights that it's leading them to, right? But then at some point they might pause and ask the question like, okay, so I found this interesting data point, but what will happen to this data point tomorrow or next quarter or next year, or depending on that, right? And then, then I could say, well, you can't really tell that from a visualization. We're just displaying kind of statistical correlations. We're showing patterns unearthed from this, usually retrospective data. So it wasn't really designed to yield predictions or other types of things that algorithms can give you, right? And so that long-winded answer might make them a bit sad, right? But then they say, yeah, okay, but I've heard about all these cool algorithms out there that can do these things and get me high accuracy predictions and get me ways at accessing my data before. And then, I could respond saying, well, yeah, but there are these black box algorithms and they might get you these high accuracy scores, but you'll have no idea what's coming out of them, right? And so after making lots of data explorers a little bit sad with these answers, I thought, okay, how can data visualization start helping and providing insights into what these algorithms are so we can further empower people to do the type of data analysis they want to do in today's world? So today I'm going to be talking about kind of 3 different projects that kind of deal with 3 different types of classes of algorithms broadly. I'll start the first part of the talk talking about one such interface to making sense out of predictions. So work with a predictive algorithm and show how we can actually help users better understand the results of predictions happening. After that, I'll follow up with another type of algorithm, clustering. So lots of people like to cluster together, find groups of data that's relevant to other groups of data. But then there's lots of choices of, okay, which clustering algorithm do you use? How do you parameterize it? All these types of questions. And so we'll kind of talk about interfaces to help make sense out of those types of algorithms. And finally, if we have time, I'll also talk about some approaches. Now there's all this hype around deep learning and all these fancy neural architectures. And of course, those are even more complex models. And so how do you help make sense out of those? And in particular, what I'll focus on during this talk is, okay, if the algorithm goes wrong, how do you fix it when you have this really complicated architecture where lots of things can go wrong at different steps? So this is kind of the outline of today. And again, it's a nice small group here. So if you have questions along the way, feel free to interrupt, and we can make this as interactive as you would like. But we'll start with predictive algorithms. Now, since I was told that there's so many different departments and lots of interdisciplinary collaborations happening here, I thought I would actually just begin by giving just a 2-minute intro, a very naive introduction to how a predictive algorithm works. So over the past handful of years, I've been dealing a lot of working on problems motivated by things in the healthcare space. So working with clinicians and clinical researchers, trying to understand how we can leverage data that's being collected about patients to better give them treatments in the future. So for this first example, I'll just motivate it by kind of assuming that we're trying to predict if a patient is going to have a certain type of disease. And again, I'm purposely making this kind of silly and naive, but just to illustrate how a predictive algorithm works. But imagine we have 8 patients here, each represented by an emoji, and the ones with the green circle around them are the healthy patients. The 4 on the right that have a red circle around them are the unhealthy patients. And we're going to use their data to basically train a prediction algorithm so we can kind of be able to predict future patients. If they're like these patients, maybe we can get a guess if they're going to be sick or healthy, right? And so we might collect lots of data about each of these patients. That's the first step, right? Getting our ground truth data sets ready. And so maybe we can count maybe the number of times each of them were diagnosed with diabetes or other disease. What is their body mass index? What is their glucose level? And these features probably seem relevant. And then there might also be features that might not seem as relevant, like can we see if they have teeth in their emoji, or can we see if they have eyebrows, right? Things we can collect lots and lots and lots of data about each of these patients, and we can feed them into a predictive algorithm and see what comes out, right? So typically the predictive modeling process has basically 5 different stages. And again, I'll go through this relatively quick, but just to give an overview so we're all kind of on the same page. But typically what you first have to do is something that you can call the cohort construction or the labeling, where basically you have to kind of define who are the patients that are sick, who are the patients that are healthy, and without properly defining these kind of cohorts or labels, then the prediction is not going to be accurate. And so again, if we have to figure out a way to kind of determine who are the sick ones versus the healthy ones, who are the controls, who are the cases in this example. So that's one part of the problem. Then after that, we have to kind of assemble all of our features. Now, feature construction is an often overlooked part of this population. How do you gather all the features together to combine them? I'm going to kind of overlook this here as well, but just imagine we have somehow assembled from lots of different data sources all these features about these patients, and we're just going to keep them and throw them into the algorithm later. Then typically what you'll do is something to ensure that your prediction is robust. You'll do cross-validation, so we'll split some of these patients into a training set, some of these patients into an evaluation set, and then we'll kind of mix and match these groups and keep running the model multiple times and see if the prediction holds true over all these different types of cross-validation groups. Another important step is feature selection. So not all of these features are important. So oftentimes to make the models a bit simpler, you'll kind of remove the less important features. So how do you figure that out? How do you do that is an important start of the process. And then finally, after that is classification. We have this evaluation set. These patients we want to predict if they're healthy or not. We'll get our prediction label. And then if we're using retrospective data, we'll also have the ground truth. And then we'll kind of see, OK, how often was our algorithm right versus wrong? And that will kind of be our accuracy score. So that's kind of a really quick 2-minute introduction to how predictive modeling works, essentially. And I would argue that visualization can have a role in all different aspects of this process. And I've built a variety of tools, and I'm not going to talk about all of these today, but for helping the labeling or the cohort definition at the beginning, we built some tools to help people ensure. Because again, if you don't have quality data going into your prediction, you're not going to have quality predictions coming out. And we've also built some tools to help with the more complicated aspects of modeling, like feature selection. But what I'm going to focus today is really at the end, this model interpretability. So once we have our prediction, let's say we've somehow done a really good job at each 5 of these steps. We have a predictive model that's giving us high accuracy. We're very happy. But again, we get to the stage of, OK, the results seem good. We have a really high AUC score. But what does it mean? What is the model doing? And again, without being able to explain that, the domain experts can be a little upset. So what we tried to do was we tried to build a tool. And this one that I'll be showing you right now is called Prospector. We published this back in CHCI 2016, where we really started being motivated by interviewing lots of different types of data scientists and domain experts that kind of rely on predictive models. And typically they would say is once they would have someone, either they would build a model or they would have someone deliver them a predictive model, they would typically the only information that they get about their model would often be kind of this accuracy score. And then also maybe they would get kind of simply a list of top features and weights. And so they were able to kind of inspect the model a little bit by seeing kind of which features corresponded to the prediction in a way. But they often wanted more information about really what was happening underneath the hood of these complex models. And so it wasn't that the people delivering these models weren't trying to deliver and summarize the models in a more effective way. It's just that is a really hard problem. And so what our issues that we wanted to address with this work was we wanted to understand, okay, not just what features impact the prediction, but even what range of values of each feature. So each of these features can have, positive values, negative values, and so on. They're going to affect the prediction different scores. So we need to know more than just the feature and its impact. And we also wanted to provide kind of an exploratory interface to let people kind of interact with the model and test different hypotheses that they might have not, they might have wanted to explore. And again, just having an output of a prediction wouldn't allow them to do that. So we leveraged this concept that was kind of popular in the data science community among some people called partial dependence. And again, it's kind of this simple technique, but it's kind of one way to probe how important a feature is to a prediction. And so again, we have our patients here. And again, the 1-minute introduction to partial dependence is, okay, we have our predictions here at the bottom. So we can kind of see the left on the 4 are correctly predicting with healthy and H. And on the right at the bottom, we have to see the 4 patients on the right are correctly being predicted as being sick. So right now, 4 out of 8 are being predicted 6. We feel good about that because we know the ground truth at the top, this aligns very well. But what happens if we kind of want to understand how, let's say, body mass index, BMI, affects this prediction? What we can do is we can use this thing called partial dependence, where essentially we would say, okay, we're just going to set everyone's BMI to 20. Leave all their other features the same, then feed these new kind of synthetic patients into our algorithm and see how the prediction changes. And if we do this, and again, this is an extreme example, but if we do this, now suddenly the left 6 patients will be predicted as healthy and the right 2 will be predicted as sick. So this feature would be really important if it actually changed the prediction of those 2 patients, right? And again, we could do the same, iterate for all useful values of BMI. So now we could try 25, see the results. We get the left 3 are sick, the right 5 are not. Then we do 30, the left 1 most person is healthy, the rest are sick, and so on. And so we get a very, very, very different type of data, or different types of predictions just by changing this one feature alone. And so what they typically do is they would typically plot this along a curve called a partial dependence plot, where basically we would see that the risk goes from 0 to 1, so 1 is being highest, 0 being lowest, and it goes depending on the value of BMI. And again, this is a simplistic example. It would go up really high as BMI got high, and it would go down really low as BMI got low, right? And so if the model was very dependent on the one feature, you might get a curve that looks like this. And so, so that was one way to start examining how things looked. So we kind of built an interactive partial dependence tool. There wasn't really too much out there on the internet, but we wanted to go a little bit further and kind of leverage this kind of calculation to let actually people kind of explore the data. So the way it works, and then I'll jump into the demo, is essentially if we have one specific patient, and this is the patient's values, let's say we want to see how this patient would differ depending on if their BMI value would differ. And so again, we have this concept of partial dependence. So could we just turn each of these features into basically a slider, let the user kind of control and move these things around and then see how the prediction would change? So could we drag BMI down and glucose down, see how the model would respond to a patient that was kind of like our patient, but now has slightly different results. And this will kind of let us test the robustness of the model itself. We could start hypothesizing of how important is this one feature for this patient. And if it's not responding in ways that we would think make clinical sense or make sense, then maybe we would think about, okay, what's going wrong in the model? So in our interface, which I'll jump to right now, we basically condensed this kind of line partial dependence plot into basically a single slider, where areas of the slider that are blue means that if you'd go in that direction, prediction would go way down. If red implies that the prediction would go higher, and so it's kind of compressed this information into kind of one plot using colors. And this would make it easier to fit a lot of multiple features on the screen at once. So I won't go into the details, but we did this with a handful of data scientists working with our tool for 4 months that were trying to really understand how predicting the onset of diabetes. And again, there's more stories of these insights in the paper, but what I'll kind of just show is how the tool works. So this is kind of what the interface looks like. And this is a complex interface, I will admit that. It was really designed for kind of the experts in kind of predictive modeling and the domain expertise. But nonetheless, I'll try to walk you through it in a short amount of time. And basically what we have on the left are each of these colorful kind of partial dependence plots on the left. So each feature kind of gets its own line, so we can see body mass index and glucose, the types of features we've seen on the previous slides. On the right-hand side, we see the traditional partial dependence plot, because this is what data scientists were kind of used to seeing. But we kind of, again, tried to make this a little bit more interactive. So what we can do is we can select a feature like BMI. And again, this particular patient, this is one patient I'm showing here. And right now, this patient's, according to the model and according to its just input features from the data set, says that this patient has a risk score of 0.71. So again, 1 is the highest, 0 is the lowest, and so this patient is pretty risky for getting this disease, right, according to the model. So what we can see is on the left, all of these patient values for each of the features. So that's kind of what we see in the circle here. So this patient has a BMI of 33 and a glucose level of 96 and something like that, right? So all these different things. But again, each of these features now become sliders. So essentially, if we wanted to understand how the model would predict this patient if he had a slightly different BMI, we could just start dragging it to the left or the right and seeing how this risk score goes up or down. So again, if you look at the current thing on the top right, you'll see that now this patient has a much lower risk by simply dragging this one feature around. And so again, this let the domain experts and the data scientists, start to reflect on, is the model behaving as they would expect? Is there too much, is this model prioritizing this one feature too much or not enough, and so on? And so of course we could do this for multiple features. We could look at the relationship between glucose, how the glucose level matters more or less depending on how you change BMI and so on. So led us to kind of start inspecting how features contributed to this prediction and if it did things in responsible ways or not. The one thing I want to show before I jump on to, further is that we also wanted to make it a little bit easier for them to kind of find features that were kind of impacting the risk score the most. So we simply kind of built two buttons like sort the features by increased risk or decreased risk. And so if I just simply right now click the decreased risk button, it's going to sort all of these features according to the ones that would be the lower this patient's risk the most by essentially moving the slider the least. And it kind of recommends a value to kind of change it if you wanted to decrease this patient's risk the most by just changing one particular value. So it kind of lets you kind of explore the most impactful features and kind of gives you a recommendation of what feature, what number to jump to get that most risk. So essentially it looks for kind of like the plateaus in the region. So you could go down really high by just moving a little bit, and it would take you to that area. So it gave a little bit way to kind of search through this high dimensional space of having lots of different types of features. And so again, with that said, we do have, there are lots of different features. In this particular interface, you would just kind of scroll endlessly until you could see them all. But nonetheless, we tried to give some way to kind of navigate and understand the impact. So I think this process worked really well if the features were understandable and you kind of wanted to test certain features that were relevant to your kind of prediction task. So right now, the main thing I wanted to convey about this is that using tools and concepts like partial dependence, it can be effective for allowing some interpretation and comparing kind of more complex machine learning models. This tool was actually built to be kind of like agnostic to the model, so it kind of treats it as a black box, so whatever comes in and out. So this supports very simple things like linear regression or more complicated models like random forest or even deep learning things. But nonetheless, it let you kind of explore and compare multiple models at once. I didn't show the comparison stuff today. But really what we tried to do was we tried to let people kind of understand how the model can behave based upon the inputs they care about. So with that said, I'm going to move to the next type of algorithm. Are there any questions or anything for clarification at this point? Yeah?
It's amazing that you were able to get these data scientists to use this for 4 months for a longitudinal study. How did you get them to do it?
Yeah, I mean, part of it was they didn't have any other tools available to do it, right? It was something they've been wanting to do. And so that's actually kind of gets to a philosophy of research that I've been trying to do since my PhD. So oftentimes we can build visualization tools, but they're kind of exploratory in nature. So there's no like good way of evaluating them. It's really hard to simulate in kind of a controlled study of, okay, if I give them this, will they be able to find that nugget of information or not? It's really hard to kind of replicate that. So my strategy is, okay, let's build tools that people actually want to use. So hopefully, if no one wants to use your tool, then you're probably not, you probably aren't working on the right problem, right? But if you can get them to use a tool and kind of study kind of qualitatively over a period of months and really try to kind of ask them to kind of record kind of stories of their success and also stories of frustration, it also helps you make your tools a lot better too. So really, I mean, but ultimately it comes down to finding motivated users. And in this particular case, people whose job depended on kind of delivering predictive models and getting doctors to want to buy into the model and convincing doctors that these made sense to deploy. They needed something, and so we were happy to fulfill that goal. But yeah, but certainly they were kind of, some of those users were involved throughout the design process and then the evaluation as well. So we were able to support their needs by understanding what they were from the beginning. Yeah, yeah.
It's really interesting to use the medical domain as an example. Are there other types of domains you've been working with using this kind of tool?
Yeah. So I mean, really, this tool is pretty domain agnostic in the sense that it'll handle predictions of anything. So we've had people use it for, financial type stuff. We've had people use it for predicting, ratings of movies and things like that. So really, anything that involves kind of some input features and that you can do a prediction for, then the tool supports. But the only ones that we've kind of studied thoroughly ourselves was these medical domain people, but we believe it extends well. Yeah.
Do you have any patient input into the model, and do you have any sense of how patients would respond to this? And it might be a motivator.
Yeah. So we had thought about, so we've done some anecdotal stuff in that area of how we could, so if you would see that, okay, if you just lowered your BMI a little bit, you could be much healthier. But again, we didn't want to go too far down that path because, again, what we're showing here isn't necessarily reality, but what the model thinks reality is. And so there are these kind of higher level questions of, okay, should we be telling patients to do something that the model thinks is good, but maybe really the clinician should be in charge of making those decisions and so on. So we're still trying to figure out kind of what level, and actually some of our ongoing work right now is actually starting to study that. So I don't have any results now, but I think that's a really important future direction, is how do you not just empower maybe the clinicians trying to make a decision about a patient, but also empower the patients to make better decisions too. Because a lot of these features too, by the way, which I kind of ignored, like some of these aren't very actionable, right? Or not actionable by the clinician. They can't just order a medication. I mean, some of these are medications, but some of them are things that require lifestyle changes or other things, and so that's a really good, interesting direction. So hopefully I'll have some results to share about that soon. Yeah.
So I like how you are able to sort by the most impactful features.
Mm-hmm.
Have you looked at other ways of trying to visualize, let's say you have hundreds or
Mm-hmm.
thousands of features, and you looked at different ways of putting those on the screen?
Yeah, we have. And so you'll see some of that come up in some of the other demos that I'll show later today. But yeah, that is a really challenging question of how do you deal with so many dimensions? And especially here, this example, even though there were hundreds of features, that's still sometimes relatively small by some people's standards. And so if you start thinking about other things, so you'll see an example later when we're actually dealing with text data where you have this endless space. And so we can maybe come back to that at that point. But good question, yeah.
I think this is related, but you're kind of asking a human to navigate
Yeah.
high dimensional space.
Mm-hmm.
And domain expertise can give you a certain way. I'm sure you're going to look at clustering sort of things and principal components sort of analysis, stuff like that. It's a tough way to go to ask somebody to navigate.
Yeah. So certainly these tools did require some training, both on the part of the domain experts and even the data scientists. But again, once you kind of show them some examples of what type of insight it can lead to, they're often, again, usually, if they care enough, they're well motivated to learn. But yeah, definitely it is complex. They're not used to. And so especially me presenting a system like this in a few minutes, it's probably hard to convey how it all works. But hopefully I at least gave you, convinced you a little bit, but that it was useful. But yeah, but it's certainly a complex space. Yeah.
Do you need any FDA approval for such software? What the regulation is? Most patients just using it on their own risk?
Yeah. So here we were doing it in kind of a research setting where we weren't actually impacting patient care. So in that sense, it wasn't needed. But certainly, if we wanted to kind of deploy this and operationalize this, and sell this as a tool to how better to treat patients, then certainly you'd have to go through that process. But we kind of used it in kind of a more paraclinical setting. But yeah, that's a good question. Okay. Oh, yes, one more. Yeah.
IBM's Watson was repurposed to provide medical services. And from what I've read, it's been spectacularly unsuccessful in doing so. How is what you're doing much better than theirs?
It's different. So I will say, this was briefly mentioned in the introduction, but I was at IBM for a handful of years. And so some of this work was not actually part of Watson, but kind of, I guess, complementary, you could say. But yeah, I mean, I think the overall, so our approach was not kind of taking data from medical literature and trying to answer questions that clinicians might want to ask about medical literature, but rather we were taking actual patient data. So we worked together relationships with the various hospitals and healthcare providers to get access to their patient data. And the goal was, is if you gave us access to this, we would build tools like this that would help you kind of understand it better. And so there are some high-level similarities between what the Watson thing was and that this was, but they kind of were tackling kind of different problems. Again, the Watson stuff was really about asking a question to from a large database of basically text, scientific papers. Okay, how do you treat this type of cancer? And then it would give that answer. Whereas this is kind of more kind of exploring kind of actual patient data. But there are ways that could be merged, but we never went forward with that. Yeah. I'd happy to talk more about that offline if you're curious. Yeah. Okay, so predictions are one type of algorithms that exist, but I'll bring up these smiley faces again. We'd show people, they'd be very happy about them, but then they'd ask a question like, okay, I found this really interesting patient. Are there other patients like this one? And then I'd say, well, you can't tell that from this visualization, but because it's just about understanding the prediction, but could we do it? And say like, well, I've heard about these clustering algorithms. Could we somehow cluster all the patients according to some clustering algorithm, find meaningful subgroups of patients? And then I say, yeah, those techniques exist, but how do you choose what clustering algorithm? How do you choose what parameters, what number of clusters to do that, and so on? And so again, that led us to the next project of really trying to think more deeply about making sense out of clustering algorithms. So me and my colleagues, we came up with a system called Cluster Vision that was published at VAST in 2017. And this is a system, again, designed for kind of data scientists and researchers, so a little bit more complex than some of my past work. But again, the idea is letting people actually figure out what type of clustering they should use. And so the reason why that's a challenge is, again, if I show you an example like this, and this is just some, essentially random data points projected into 2 dimensions. So this is high dimensional data using a projection technique like t-SNE to project on the screen. And you might say, yeah, this might be a good clustering technique. So right now I'm coloring each cluster with a unique color. You might say, yeah, this looks pretty good because, according to this projection, these points are separated from each other, and now they each seem to have some color. But again, there's a question of, okay, but what about if you wanted bigger groups or smaller groups, or the types of nuances you're trying to find from these clusters? You might want really smaller level things that are very specific to each other or not. And basically, there's lots of different ways to compute clustering, and these are all real examples of trying out real algorithms with different parameters and kind of breaking down these data points into multiple groups. And so this really just kind of led us to go back to different data scientists and essentially ask them, okay, so what clustering algorithm do you use when you try to do this report? And of course, each data scientist you would talk to would kind of have their own kind of favorite. They'd be basic things like k-means or more advanced things. And really, they kind of all had their own favorite things. And when you ask them and press them, okay, why do you use this technique? They'd be like, well, I've used it before and it worked pretty well, so I'm happy to kind of use it again. They didn't often have very satisfying answers for kind of why do they use them. And furthermore, the same thing would be true of if I asked them, okay, what parameters did you choose to plug into it? How did you know to tell it that you wanted 5 clusters? Or how did you know to specify the distance metric like that? And again, they would often say it involved a lot of trial and error. And so we thought, okay, well, if we have data that's messy like this, and you get clustering results that look like this, is this good or bad or so on? It's a hard question to answer. And so what we wanted to do was we wanted to figure out how can we measure quality. So we asked those same data scientists, how do you measure quality in clustering? And some of them would say, well, it kind of looks good to me, so I'm happy to use it. Some others would actually use these kind of quality metrics presented in the literature. So again, these are purely statistical measures that kind of measure kind of the cohesiveness of all the different clusters according to properties and come up with a quality metric. And so there's lots of metrics out there that do this. This is some of them. So we thought, okay, could we kind of combine all of this stuff in one interface to at least make it easier for people to kind of browse? And so that's what we see here in this tool, is simply a way to kind of compare lots of different clustering results. So essentially what we do is kind of brute force behind the scenes. We try out lots of different clustering algorithms, lots of different parameters, lots of different quality metrics, and try to present the top best ones to the users, but then ultimately let them control what they're looking for. And so what we are able to do is allow users to kind of compare different results, understand why data points are being clustered together, and again, also let users kind of navigate this in a more user-driven way. So rather than just running a few different things in the command line and seeing what gets back, actually providing a visual overview of everything that could have been run. So for this example, just to simplify things, I'll move away from the medical domain, and I'm just going to use a simple kind of toy data set. So some of you might remember Bob Ross from PBS. He was on PBS when I was a kid, and essentially he was this kind of artist that would kind of make every episode he would paint something, right? And so a few years ago, 538 just decided to go watch all 403 episodes of his show and manually code each painting using 67 different features. And so like, is there a tree in the painting? Is there water in the painting? Is there certain mountains or weather in it? And basically, they're all a bunch of binary features. So this is a relatively small data set, 403 paintings by 67 features. But nonetheless, it kind of illustrates the tool without having to know too much about medical stuff. Although this project was also motivated by medical, and I'll talk a little about those results at the end. So this is the way the interface works. And for this particular data set, we're going to cluster according to a few different clustering algorithms and a bunch of different parameters. And so basically what we have on the left are the top 20 clustering results overall. And again, the users could adjust which type of algorithms you use, what are the parameters that they want to set, and so on, and kind of rerun it. But after they'd redo all this stuff, what they would see is for each clustering result, we kind of symbolize it according to two different views. You have this kind of striped bar view. So these are 3 clustering results. This first one means that since most of the bar is blue, that means that most of the data points are in a blue cluster. Everything else is in a green cluster. So that tells us there's 2 clusters in this group. So very simple. The second one has 3 clusters, a big blue, a small green, and a big yellow. And then the third one is kind of similar, slightly more in the blue, slightly less in the yellow, and so on. So that's how to read these bars on the left-hand side. And on the right side is something called a radar chart. And basically what we're showing here on each of the axes of the radar chart is according to a quality metric. So these are kind of statistical things that can be run on the clustering result to kind of tell us how cohesive or not those subgroups are. And so again, there's kind of I guess, not consensus of how useful each of these metrics are, and they kind of give different reviews. But anyways, we summarize them by running a bunch of them. And basically the way to read this chart is that you can see for 4 of the metrics, they have really high values. They're at the boundary. But for the 5th quality metric, it had a really low score, so it's towards the middle. So if you saw everything totally around it, that means it would be super high in all 5. But this one was super high in 4 of the 5, and 1 was less. And you can kind of see this pattern is a little different for the other 2. So basically, the things that are closest to the outside are the more are the higher the quality is according to those metrics. And so again, yeah, the cluster summary and the quality summary. And then what we have at the bottom is so we can select one of these clusters. And once we do that, we can see here that now we see, again, using a projection technique. So the top view is this projection technique. Again, this is pretty common for how people look at clusters. At least data scientists do it, where they basically project the high-dimensional stuff into a 2D space so we can see it. So here we're using t-SNE, but there's lots of different ways of doing that. And basically, we can see that there is this big blue group that mostly seem to be around each other, and this kind of smaller green group, which has some blue data points embedded in it for some reason. So that's the projection view at the top. And again, this is going to stay the same no matter which clustering result we use. So we're not actually trying to say that this projection technique is meaningful necessarily, but it's kind of like a common way to explore different clustering results together and be able to compare and contrast how they look without changing, having things move around the screen every time we choose a result. On the bottom part, we have two different views. We have this kind of ranked feature view. And this is basically a list of the top features. So basically, we have some techniques using statistics from ANOVA to basically determine what are the top meaningful features for why these clusters were separated apart. And we can kind of see that the top features in this example was the presence of trees and oceans and waves and things like that. So these are the features that kind of distinguish something being in the green group versus the blue group. And I'll come back to this point in a little bit. And then next to that, at the bottom of that, is this kind of, we call it a parallel trends view. It's kind of like if any of you have seen parallel coordinates, it's basically like, typically the way parallel coordinates work is you get, for each data point, you kind of draw a line through where, so each of these lines are axes. And so wherever the data point would go through, you'd kind of just draw a line through it. So this can be an effective technique for making sense out of high dimensional information by basically being able to show here like 10 dimensions at once. If you've never seen it before, I'll just try to, things to take away from it would be that we try to simplify that to summarize not showing a data point for every, not showing a line for every data point, but rather showing kind of a nice thick line for every cluster. So basically what we do is we summarize all the data points in a cluster with kind of the mean, which is this dotted line, and then for a standard deviation around it, this kind of band around it. So we can kind of see that this green cluster does seem to be a little bit different than this blue cluster. So this screenshot was taken from a famous like car data set of why cars are different. And you can kind of see that these blue cars are different. They have higher horsepower and weight than the green cars. But I'll come back to the painting and we'll see how that one looks here. So what we can see in this example is that the green cluster is higher at different features than the blue cluster. And so so we can see that a large blue cluster of paintings consist of things that have trees and conifer and deciduous, those are types of trees, right? They have trees in them, so those types of paintings kind of look like that. And then the green paintings are the ones that have things like ocean, waves, and beach, which is why you have higher values for these features. And again, you get paintings that kind of look like that, right? Okay, so that's kind of how we can get a sense out of how these clusters actually differ just from this high-level overview. There does seem to be something, the presence of features different just from this high-level view. But of course, we might want to consider other clustering results. So again, what we can do is click on a different one like here that breaks that hair has 4 clusters rather than 2. And so we can kind of see that it seemed to have broken what previously was a giant blue cluster into now 3 different clusters together. And so, okay, we have more clusters now. Are these better or worse than before? So again, we can do a similar inspection by, looking at how they look down here on the feature clustering view. Oh, I guess before I do that, I just wanted to show that you can actually inspect data points and get some more information about each data point, what its values are. We compute some statistics about it and show information about the cluster and show information about the data point itself. But in the interest of time, since I'm running behind, I'm going to kind of skip some of those details for now. The main thing I want to be able to show you is that what we can actually do is start exploring how these clusters differ from each other. You can see this red cluster seems to have high values for trees. This blue one seems to have a high value for cabins. This yellow one seems to have a high value for mountains. And so each cluster, if you'd spend some time looking at it, it would kind of they would kind of have different properties. So what I'm going to do now interactively is kind of drag and drop these features to make the clusters a little bit more easy to read. So I'm kind of rearranging the axes to make them a little bit more readable. And so again, we can kind of see that this green cluster has high values in oceans, waves, and beaches. This yellow one has mountains, conifers, trees, and the blue one has cabins, which the other ones don't too. And so we're starting to be able to see that we could actually break this bigger group that used to just be known for its trees. Now it's the presence of other things. We can also add additional features in. I'm kind of clicking on the left, adding in some more. And so again, we can kind of start exploring more features at once, and then again, start rearranging things to kind of drag them together and see that palm trees are also part of this green group, and the word structure is part of the cabin group, and so on. So you can start kind of adding more features and starting to kind of make the differences a little bit more interpretable. And so again, we'll end up with a green group that has kind of the mountain paintings, because it has high values of oceans, waves, and beaches. The red group has just lots of stuff about trees, nothing more specific than that. The blue group has trees plus cabins and structures, and then the yellow group has kind of the mountains and trees, right? And so again, illustrating this with a simple data set can show you how we can start to kind of quickly see the differences between different clusterings. And some of them might be appropriate for some type of analysis. Maybe we would want just one big tree cluster. Other times you might want a little bit more details. And then again, you could choose even more results to dig down deeper from that as well. And so what we actually did in practice was actually we kind of used this for some more serious data sets where we were actually trying to work with clinical researchers to actually find different types of groupings of patients that were previously considered to be similar, but they actually had different meaningful subgroups and different ways to treat them. I'm not going to go into the details today in the interest of time, but basically using this tool, clinicians were able to actually kind of find new types of groups, and this actually led to some medical publications. So summarizing this tool, what we really tried to do is we tried to kind of let the user kind of try out a bunch of different clustering techniques based on a variety of algorithms and parameters. So rather than having to choose one, they could just try out a lot at once. And we tried to give them a kind of an effective overview to kind of browse through all of those. And then using the system, users could kind of also explore and specify different constraints. So I didn't show that before, but if you knew a lot about a couple data points and you said, I really need these 2 data points to be in the same cluster, only show me those results that satisfied that constraint or didn't satisfy that constraint, you could do that too, and you could find kind of different types of clusterings. But that's kind of the idea, is letting users kind of browse all this cluster data in lots of different ways. Okay, so I know I went a bit fast because I'm a little behind time, but are there kind of any questions or anything about this particular work? Yeah?
You mentioned what quality metrics you were plotting?
Yeah, so I flashed them really fast on the screen when I was those questions, but yeah, they're everything from like this Kolinsky-Haribaz score to SDBW. There are kind of lots of different ones. There was a survey that was written a couple years ago that we kind of pointed to that kind of tried to rank all of them according to lots of different data sets. And so we kind of chose the top 5 based upon that research paper. But certainly there's lots of others, quality metrics. Yeah, yeah. But yeah, they're just about the clustering. And again, how do you kind of automatically measure how good a clustering is or not? And again, there's lots of controversy of if those are useful or not. So we did let users kind of rank according to them and kind of understand how a clustering would be according to all of those. But we saw in practice that our users didn't often pay attention too much to those scores. They were a way for us to kind of rank top clustering results originally, but it really kind of, it wasn't an important part of the process. And so I think we need to kind of reflect on, is there something better, a different way that we could rank them that might be even more effective for what they want. Yeah.
And you did say this, but I just missed it. How are you ranking the variables for explaining clusters? How are you doing that?
So we're using F-statistics from an ANOVA. If you want offline, I can talk more about it, but the full details are in the paper. But yeah, it's kind of a common way of actually explaining which features are important for when you do a classification task, like if you're trying to understand a prediction per se. But we just kind of leverage it for, okay, if we have this, we consider this cluster one class and this color this other class, what are the most meaningful features? So kind of similar to the feature stuff I was talking about in the last section. Yeah. Yeah.
Does the system allow for adding new metrics or making your own types of clusters? Is it dynamic in that way? Can I put in my own metric if I wanted to?
Yeah. So it's pretty easy to integrate. Essentially, you just would have to kind of wrap some functions around some Python code. So this was all, but yeah, so it is possible. We didn't totally make it as kind of extensible as one could, but it is open to that, but it kind of requires development experience as opposed to kind of having menu-driven approach. But yeah. Yeah. Yeah.
What's the architecture of your system? Is this a front end purely, or do you do all the statistics as well, or do you call different libraries sort of fail with put together?
Yeah. So there is a back end, but it wasn't designed to necessarily be the most optimal way of computing it. So it is kind of a Python-based server that's kind of running all this stuff and utilizing kind of the typical clustering algorithms that are built into the popular libraries like scikit-learn and stuff. And we did build some, we did do some things to kind of smartly parallelize these computations at once. But certainly, if you wanted to distribute this and make it a real serious tool, figuring out the right way to kind of make it even more distributed would be important. Because certainly, even on small data sets like this, running a clustering algorithm, 100 different ways does take time, right? And so typically the way how our users would use it is they would start the process, leave their machine, and come back later, right? And so that's obviously not the ideal way to do it, but yeah, that is a good. The more things you want to let the users explore, the more computation time it takes. So that is a serious kind of question that we didn't explore directly in this work, but it's important. Yeah. Yeah.
The quality of clustering depends on many hyperparameters that they for each algorithm. How would you decide about those hyperparameters?
Yeah, so in this particular approach, we kind of used a pretty naive, where we would say for each parameter that an algorithm would take in, we would look at the literature to kind of see what are reasonable value ranges for that hyperparameter, and then we would literally just try out lots of different values in that space. So it was a pretty naive brute force approach. And certainly there'd be ways to kind of optimize that. But here the contribution was more about how do you present that information effectively. But you're absolutely right. If you wanted to make this more efficient and produce higher quality clustering results without trying as many things, exhaustive things as we did, that would be an important research area. But yeah, but right now there doesn't seem to be great insights into how you would choose those values. So that is something that we're thinking about in our future research as well. Yeah.
Like the quality of different algorithms really depends on those hyperparameters.
Right.
And there are some clever techniques to tune those hyperparameters. So there are some gradient-based algorithms to train or implement those hyperparameters.
Yeah, exactly. So you could theoretically perhaps integrate some of those to try out smart values of the hyperparameters, but yeah, we didn't do that in the context of this work. But that's an important point. Yeah.
Is it also possible to fix the number of clusters I would like to find before getting the return?
You could kind of set, I want X amount or this range of clusters and only deal with those. Yeah. Okay. So when am I supposed to go until? I had a third project, but do I have time?
Yeah, you have time.
Okay, sounds good. So I'll kind of go quickly on the last project, just so I can see it and we can save some more time for questions. But again, I'll bring these emoji guys up again, and again, people would show this and they'd be happy about the insights, but then they'd say, okay, but yeah, I've also heard about all these kind of fancy neural architectures doing deep learning. Are you using those? And I would kind of respond, well, our systems are pretty much, again, agnostic to what types of models you feed into them. But of course, the more complex your model is, oftentimes the less interpretable it is. But then they would say, well, I've heard about all these deep learning techniques revolutioning the field. And I would respond by saying, well, yeah, that is true. But again, it's sometimes really hard to make them work well. So we started pushing down some work of kind of making sense out of deep learning algorithms. I'm going to show you one tool that's pretty specific. We're doing some future work that builds upon it. That isn't quite ready to share yet today. But the project I do want to share today is a tool that we presented at VAST a few months ago, where it's called sequence-to-sequence visualization, or sec-to-sec-viz. And basically what it is it's a debugging tool for one particular type of deep learning network. And I'll talk some lessons we can extend from this as well. But if you've never heard of a sequence-to-sequence model, basically it's one type of deep learning neural architecture. It's really popular and it's also pretty fascinating because you can basically translate between an arbitrary length input sequence and get out an arbitrary length output sequence. So what does that mean? It means that it's really effective for machine translation. So if you're going from German to English, you don't have to have a one-to-one word for each word, but rather you can have a long German sentence be a short English sentence or vice versa, right? It also works well in things like image capturing, right? You can take an image and you can transform that into a sequence of pixels and then end up with a caption, a totally different type of output sequence, right? And so it's popular in a lot of these applications that I listed here today. And so I don't have much time to kind of go into how a sequence-to-sequence model works, but if I hope I convince you of one thing with this slide is that it's really complex and a lot of things can go wrong in different places. So you can kind of think of it as a 5-stage process. First, you have an encoder. You have to take the input. So we're going to deal with the context of machine translation, how we can go from one language to another language. And so basically, it'll take an input word in that case and translate it and its context somehow. And so typically, if you've ever heard of an LSTM, that's typically how it's done in practice. But basically, it's a complex neural architecture just for doing the encoding stage of how we go from the input to this contextual representation, some sort of latent space. And so we have the word, and then we keep the context of that word. That's the idea. And then we have a decoder that has to transform it from this space to the new place. So again, if we're going from, we'd be going from, let's say we're trying to translate from German to English, we'd go from German to some intermediate space, and the decoder would take that intermediate space and go back to English, right? But how do these two operate with each other? You have to have another third type of model called an intention model. And basically, this is like a weighted distribution of input words to help kind of often like predict the next word or the next thing in the sequence. And this is a key part to making the model more interpretable. So we'll see this in the demo in just a second. And then the fourth part is the prediction. So, and again, this is kind of a probability distribution that helps you kind of choose the most likely next word in the translation. So we're thinking of sentences as a sequence of words. And so how do you predict what the next word will be? And it's relevant to the previous words between them. But the problem with this is that you could end up with a local decision. So again, there's other more complicated things you could do on top of it. Here we're using a beam search to basically keep a set of options alive at each stage. So it's basically 5 models all kind of shoved together, all very complex, some of them very, very complicated in our architectures. And so the question is you have something like this, where we have an input German word in blue and an output English word in yellow, and something goes wrong, how do you figure out what went wrong in the model? So all of my co-authors on this paper coincidentally speak German, except for me. So I'm not gonna use a bad German accent to read the word in the sentence in blue. But this is an example of a German to English translation sentence that was not translated correctly. So the top sentence in blue. So each word is each blue box is a word, and basically it translates roughly to the longest travel begins when it gets darkest in the streets. This was from a famous German philosopher, I've been told. But what we see is the output from the model is actually what's in yellow. And you'll notice that the word dark is not there at all. It just says the longest travel begins when it gets to the streets. That's not technically a grammatically correct sentence. And it's also missing this really important contextual word of dark, which is kind of like actually gives the sentence meaning. And so if this word is actually missing, how can we identify what went wrong? And so talking to our collaborators in the old days, if you had a role-based system, what would you do? You'd look it up in something called a phone book, and it was basically in role-based systems if something went wrong. You looked up the rule that maybe produced the incorrect result in the translation, and then you fix that rule, and then you could move on, right? But in deep learning models, there was no such rule book. So what we really tried to do was provide something similar to that, but more interactive. And so, so we basically took this complex process and tried to design a visualization interface to kind of encode each of these different steps. And I'll go quickly here, but jump into the demo in a second. But basically, we have the encoder is these blue boxes at the top. The output, the decoder is the yellow boxes there. So going from one language to another. And then we have the attention model is these lines. So we can see which words are paying attention to other words according to the attention model with these kind of lines connecting them. And then we have the predictions. For each word, we have the top K predictions of what word should be there according to the model. And then we also provide this kind of illustration of the beam search, how the beam search is keeping track of other words and other alternatives. So again, a lot of information here on the screen. And what I was going to do is I was going to jump into a live demo, but then I checked this morning and the demo was down. There is a website. I'll try to get it up and running. I didn't have time to do that this morning, but I was able to scramble on my computer and found some video clips that I can kind of that I quickly edited together. So we'll see how smoothly this goes. But basically, what I did was I had an example of when I was doing this translation from the same thing I did in the slides. Which again should translate to the longest travel begins when it gets darkest in the streets, but it's missing the word darkest. And so the way this tool kind of works, and again, I am going to go relatively fast given time, but basically the idea here is that we can start inspecting to see what is going wrong for going right or wrong in each of these steps. So really to evaluate if this model works, we'd have to see, okay, is the encoder working well? Is the decoder working well? Is the attention model working well? Is the prediction working well? And is the beam search working well? You'd have to check all those things just to see if this model is working or not. So what we can actually do is we can actually scroll down to the bottom and start looking at the encoder. This is a little hard to see on this screen, but basically for each word in this German sentence, what we see is we see the German word here, and then we kind of see what is the context around that word. We use a projection just like we did in the clustering technique, but here we're projecting the top K similar words to that. And so basically you kind of see words surrounding this word for dark and each of the other words. And then you can kind of click on a word, like we can click on dunkel, which again means dark, and we can see kind of what are all the words in context for this word. And again, what we can kind of see if we would kind of scan through other results, we would see that for the most part, it does seem like we're getting words like dunkel highlighted. That's what we're highlighting in red in each of these sentences. You get some random noise like you always see with text data, but for the most part, it seems like it is kind of capturing words related to dark in this space. So we could say, okay, that's fine, the encoder's working. We could do the same for the decoder, which I'm going to skip here. But basically, if you believe me, I'm going to say that there wasn't a problem with the encoder, a problem with the decoder. So how do we move on to the next step? And so what we can do is we can kind of scroll back up and start looking at the attention model. And so that's what we have by these kind of gray and red lines. So what I've done now is I'm actually highlighting this word to, and what the red lines that point to it are actually the words that it's paying attention to. And we can see it actually is paying attention to this word dunkel, the word that means dark, but for some reason, it's not showing up as the most highest predicted word. So that's kind of interesting, but nonetheless, this gives us a clue that the attention model is probably working well. So now we can look at the predictions, and we can kind of see that the top 5 predictions for this coming after this word gets are to, dark, buried, into, and in. And so we see the word dark here is actually here as well. So that's pretty good. So it seems like at least dark was a relatively high prediction, but for some reason it wasn't chosen to come after the word gets, instead the word to came after the word gets. So again, we could explore this beam search and see that for some reason the beam search was never looking at the word dark. So this is actually the problem with our model. Something about the beam search wasn't working together, and then actually using this kind of introspection, the model developers were kind of able to fix the problem with the beam search and actually correct that and make the model better. So I realized this was really complicated and I went way too fast, but basically the idea that I hopefully conveyed, at least from this example, is that these deep learning models, especially something complex like a sequence-to-sequence model, they're really complex. There's lots of models feeding into other models, and so debugging them is really hard. So although they've kind of can give you really high accuracy scores, we really need to build better tools to help people kind of better allow introspection of them, because if you're going to start deploying them on very important things, you need ways to kind of verify what's going on and not. So this tool, which is actually the demo which we'll all fix and have it up and running later today, along with the source code and all the paper, are available at this website. And hopefully I've convinced you that it helps. We've shown some examples of how it can really help model developers identify the cause of errors in complex models. So with that today, I've showed you kind of 3 different types of algorithms: predictive algorithms, clustering algorithms, and deep learning algorithms. But I guess the main takeaways I want to say is that, of course, yes, data is complex and necessary, and visualization can provide a much needed gap for just making sense of data. But again, a lot of these exploratory tools don't address kind of these algorithmic desires of people wanting to do prediction or clustering or deep learning for a variety of things. So hopefully I've at least convinced you that there can be a strong role for visualization to help these algorithmic tasks. I didn't really have a chance today to talk about kind of the implications of this work, how it can help people kind of understand how good or bad a model is, both from from a quality perspective and an ethical perspective, and all these different types of things. But I'm hoping we'll touch upon those issues throughout the rest of the workshop. So with that said, I'll stop talking and take any more questions. Thank you. Yeah.
So I have a question regarding the sequence to sequence.
Mm-hmm.
When you, the example that you gave, when you fix the problem with dark,
Mm-hmm.
and the model is adjusted to produce the correct sentence, for example, wouldn't that also alter the translation for other sentences?
Yeah.
How do you make sure that it doesn't have ill effects?
Yeah. So some of our work has been trying to kind of keep track of those changes and actually visualize the impact of new changes. So some of our follow-up work is actually kind of maintaining states of all these models and the fixes you might do. And then how do you kind of provide an overview of all these different models and actually figure out which one is the best. Because again, when you start fixing small changes, it can have implications otherwise. So that is a huge body of work. We have some work we just submitted a few weeks ago about that, but it's, again, still only a low-hanging fruit. I think it's a really important problem and hope to work in that area in the future. Yeah.
So when you think about the title of the workshop, right, and the role of algorithms in making you think versus, for instance, the role of visualization, I wonder sort of if you could postulate or wax eloquent about, to what extent do you see the role of the algorithm in facilitating critical thinking here, as compared to, for instance, the visualization?
visualizations on top.
Mm-hmm. So yeah, so most of this work is really focused on, okay, people are relying on algorithms for data analysis, and they often don't have any, they might not even understand what the algorithm is doing. They just know that it's a tool that they have access to and they run it and they can get some results. And oftentimes, based on our interviews, they often trust the results without thinking deeper about it. So our approach has been really, okay, can we somehow kind of provide some insights into what the algorithm is doing so then they can think more deeply about, is it appropriate or not? Is it doing the right thing or not? Is it showing something funny? And if so, why is it? And is it a problem with the algorithm? Is it a problem with the data? And so on. So I didn't have a chance to talk too much about that specifically here, but certainly that was kind of the overall motivation. Now, I think a lot of this work is still, you could say, in its initial phases where it's really designed for like the model developers, since they're the ones that are kind of in charge of building these models right now in a lot of these systems. So we at least try to provide them some tools, but certainly we haven't gone down the path yet of really focusing on kind of the consumer of these models and how they sometimes have to make decisions about the results of models, and yet they have no idea. And so do you want to provide them something like this? Probably not, but you probably want to provide them something that gets them there. And so that's also what a lot of kind of my current work is trying to figure out, is how do you kind of get some of this complex data, which is still we've simplified it a little bit, but it's still really complex. How do you present it in a way to a person making a hard decision without sacrificing all the complexity that really went in the decision, right? If you provide, there are some approaches that are out there that try to provide some explanations of models using kind of simplified models, but those can be misleading in a lot of ways. And so we're really trying to figure out that tension, and I think that's a really important open research challenge that I don't have any answers to, but I'm hoping that's going to occupy my agenda for years to come. Yeah. Yeah.
So following up on that really kind of big picture question, so like, what does it mean to be explainable? Like,
yeah.
How do you know when you've achieved explainability, right? So we read your prospector paper in the reading group we had for the workshop this semester. In your paper, you list some questions, like questions the doctors were able to answer about the model, right, given your tool, right? And so that seemed like one definition of explainability was you can answer these 5 questions.
Yeah.
Right? And they were pretty specific questions about the domain.
Yeah.
But is there a broader way to think about how you know when you've achieved explainability?
Yeah. You know, that's an interesting question that we've thought about. I'll see if I can think of a succinct answer that brings some value. But basically, it's kind of like also, it comes back to, the type of question you ask about, is a visualization useful or not, right? Like, what are the types of questions you want to ask with a visualization? It's kind of a similar kind of, I never had a good, like, non-flaky answer for that. And I feel like the same thing is true about explainable, because really you can ask, there's such a broad way that you could satisfy or not satisfy someone. They might want to ask very specific questions. They might just go on one. So what we're trying to do, and again, I don't know if this approach is going to work now, but we're working on some initial exploratory work trying to investigate this by looking at kind of one common type of algorithm that tries to predict, so for image classification, you have an image, you have some algorithms that say what's in that image, and there's been a variety of explanation approaches that have been tried to show that maybe you highlight the parts of the image that are responsible for that prediction and so on. And so what we're doing now is we're starting to build this platform where we can actually ask users to kind of like give feedback on do they like this explanation or not, and through using a bunch of different techniques. So we're kind of taking like a crowdsourced approach to seeing, can we somehow quantify explainability by just letting lots of users comment on if it's explainable or not? I don't know if it's going to work or not. It's kind of a more exploratory project that I don't have super high hopes for, but I think it's a fun project to work on. But that's at least one direction we're trying to think about. If we can give it to lots of people and they're all satisfied, then maybe that tells us something. That's certainly a lot better than what times you see in some some papers, like a machine learning paper that would just show one visualization and say, hey, our model works because look, there's a dog in this picture and there's a dog. And so can we provide some sort of some resource for someone that wants to actually figure out if their model is working well or not, and can we somehow leverage humans to do that? But I don't know if it'll scale. There's so many neurons in the deep learning network, and getting them to look at every type of thing that gets classified in every so I don't know, but yeah. But we're thinking about that. But I would love to chat more about that throughout the context of this workshop. Yeah.
Just a quick follow-up on that. I feel like we could also, like the explainability can also differ based on whether an expert is using these tools versus, say, a novice user. So I wonder, like you were mentioning last night at dinner, that you're teaching this class of students on data science. So I wonder some of these tools, if they're used by students, and then what do they where they have no idea how clustering algorithms work, but this could be one way of figuring it out and maybe seeing from the perspective of a novice data scientist, per se, like what does explainability mean for them?
Right. Yeah, that's a really good question. And so yeah, one of the things that I have dreams of doing, and I've done this a little bit in my own courses, where we try to, I'll sometimes use these tools to kind of explain what the algorithm is doing as I'm teaching the algorithm. But again, they weren't really designed for that process, but there are a lot of principles that's shared. So I am trying to think about, can we use these to actually kind of enhance the curriculum of the data science courses around and let people kind of understand better, and kind of what are the things you need to include in that to make it explainable to not a domain expert, not a data expert, but someone that's just trying to learn the concepts. And so there are some, I think there is a lot of common things that we've done that we could extract, but I think there's also a whole other layer that we'd probably want to do to expand that. Yeah, it's a really good question. Yeah.
All right. Well, thank you very much, Adam.
Thank you.
So how about we take a quick break, and we'll be